The antiderivative of tangent of x is natural log of secant of x plus c. All right. I don't know why I have my marker so thick. It's fine, I guess. And I can just kind of justify that for you here. So if I say f of x is equal to the natural log of the secant of x, well, I would have loved to be able to justify that for you, but for whatever reason, that's like the one function Desmos can't handle. Oh, I got to put parentheses around. Oh, okay. That's weird. So it won't treat the absolute value as fencing, like parentheses, which is kind of strange, but it is what it is. So that would be my original function. I don't really need to see that as much as I need to see that function's derivative. Which, if you know the tangent function, you would recognize this as being that, right? But if not, you could put in the tangent function and do a quick compare contrast. Tangent and the derivative function are mapping to the same location. So we know we're onto something here, all right? Yeah, that isn't really a proof or a justification or anything. It's more a demonstration that what I just told you is correct. But really the benefit of being able to do something like this, you know, this whole idea of popping it into Desmos is so that when you suspect that you're on to the right answer, you can check your work and make sure that everything's up to snuff, right? So whatever you have as your suspected antiderivative, this bad boy here, should go in as the original function. Its derivative should be the integrand, right? So we're working backwards, literally, right? So at this point, because you'd have to know something like U substitution in order to understand where that rule came from. Yeah, exactly. So the question was, so would one way of thinking of an antiderivative is thinking backwards, like how did I get the answer and go backward? Yeah, exactly. All right. Very good. All right. So at this point, you're just believing me that it's true. All right. The other ones we were able to justify from our knowledge of derivatives, but this little section here, these are just rules you got to know it, at least at this point. All right. So secant has an antiderivative of the natural log of secant x plus tangent x plus c. Same idea. If I were to take the derivative of the natural log of secant of x plus tangent of x, I could pop that in easily enough. Take a look at its derivative, and then take a look at the secant function. Whether I type it in or just grab the function itself. Here's the secant function. Here's the derivative function. They're mapping to the same location. All right. So, you know, it's at least true in the sense of, you know, like on this interval, it's mapping to the same location. If it's and it's a periodic function, so if it's mapping to the same locations on this interval, we can be reasonably assured that it's going to map to the same locations on every interval. All right. Now, we did learn for derivatives that there is a relationship between a function and its cofunction. All right. So a derivative of a trig function, if you know that value, or that function, if you know, like for example, the derivative of sine is cosine, right? So I'll take you kind of down that road here. For example, the derivative with respect to x of the sine of x is equal to cosine of x, right? The cofunction of sine is cosine. That you just, whenever you're talking about cofunctions, you're just slapping on a co or taking away a co. All right. So the relationship is cofunctions have derivatives that are negative cofunctions. All right. So cofunctions have derivatives that are negative cofunctions. Right? So sine and cosine are cofunctions of one another. All right? So if I want the derivative of cosine, all I have to do is take the derivative of sine, negate it, and apply that negation to the cofunction. Right? And again, the cofunction is just either slapping on a co or removing a co, depending on what's there. So this is already a cosine, so I would remove the co and make it sine, but I'd also negate it. Right? And so that would give us the derivative of cosine is negative sine. So it's like, okay, cool. That's, fun fact of the day. How does that help us here? It also works in reverse. Right? Because I have it somewhere, the antiderivative of sine is negative cosine plus c, but negative cosine is the heart of it. All right. Sine and cosines are cofunctions of one another. So their antiderivatives would be negative cofunctions. All right. Secant squared and cosecant squared, those are cofunctions. Their antiderivatives are negative cofunctions of one another. Take the tangent, slap on a co and negate it, and you have the antiderivative of cosecant squared, right? So if you know these two antiderivatives, then you know these two, because the cosecant is the cofunction of secant. So this would have to be negative cosecant x minus cotangent x by that reasoning. So we would just test this out and see if it's true. All right. So I would put my antiderivative in. Well, that's fun looking. All right. So that's negative the natural log of cosecant x minus cotangent of x. Oh, I'm sorry, plus cotangent of x. I don't know why I wrote a minus there. Plus cotangent of x. All right. So then the derivative of that is this graph. So that should be the same as cosecant. Right? By that same reasoning. Right? And you see that they are the same. All right. So the same graph. So then by that same reasoning, I could find the antiderivative of cotangent. If I know the antiderivative of tangent, the negative cofunction now, because you have a negative coefficient on the log, there's actually other ways that you could represent this. So log rules, they make things simpler, but also they kind of make things sometimes a little bit more confusing, because this negative here, whereas in this case, the negative might not have served to make things any simpler, or at least not at first glance. This one, if I make it an exponent, this would become the natural log of cosecant x raised to the negative first power. So I'm due for a resize here. But when you raise a ratio to a negative power, that's essentially telling you to take the reciprocal of that ratio. All right. So the reciprocal of cosecant is actually sine. So this, in theory, would be the natural log of the absolute value of the sine of x. All right, so that's what I would test out and see. So is the natural log of the derivative, the absolute value of the sine of x equivalent to the derivative of that equivalent to cotangent of x. All right, so I might as well just wipe this out. A little switcherooski here. F of x all right, so ln parentheses absolute for some reason sine of x, a funky looking graph right there, but that should be equivalent to cotangent of x. All right, so cotangent of x, turn off the original function. These two graphs should map to the same location, and they do. All right, now if I put in the negative natural log of cosecant x plus c, it would give me the same thing, right? But also I wanted to mention, let's say, for example, I did have that. Let's say, for example, I had the CSC, and I suspected that this was the antiderivative, and for whatever reason, I missed the negative sign, all right? You could actually pick that up using the Desmos check, because again, we're not interested in what the original function looks like. We're interested in what the derivative function looks like, all right? So the derivative function looks like this, but the integrand is that. It's a reversal, all right? So typically, at least in this course, because we're only working with, like I said, basic integration, the worst case scenario is that you're only going to be off by a constant multiple, right? So some coefficient that you don't, that you're not accounting for. So most of the time, people will know the heart of the antiderivative, the guts of it, if you will. They just won't know necessarily what the coefficient ought to be. So like in this case, I'd look at it and say, oh, I'm not sure if it's positive or negative. Well, it didn't match up, so it's probably a negative. So I could just pop in a negative there and give it a shot. The alternative to that, and then it works out. The alternative to that is to put some slider value there. So make a slider and then slide that slider until you get your two curves to match up. And there should be an instance, at least for the problems that we're going to do, where they match up perfectly. They not quite, getting closer. It's at -1 where it matches up perfectly. So you know the leading coefficient here has to be a -1. All right. So it's more trial and error than anything else, but it's trial and error with a little bit of basic knowledge involved. Right. Because most of the time when people when they mess up something like this, it's usually based off of knowledge of a coefficient, and that could be pretty unforgiving when you're dealing with a multiple choice question on an assessment. Right? So it's a good way to check it at a minimum. Now on the next page, we're asked to apply all these rules, which can be easy. It can be very easy in some instances, and can be very challenging in others, obviously. All right, but they're all going to come back. Every problem I give you in this course is going to come back to this page of rules. All right. So if you know or have access to this information, you're in good shape. Before Calc 2, I recommend that you commit all of this to memory. All right. Just treat it like you would the unit circle. For those of you who memorize the unit circle, it's got that level of importance. You will have. You'll be well prepared going into Calc 2 if you have that stuff down pat. All right. So the first thing I noticed when I look at number 1 is it doesn't look anything like any of the problems that were on the previous page. Right. But it's a ratio. And so I can move an expression from one part of the ratio to another if I negate the exponent. So I'm going to rewrite this as the antiderivative of x to the -4th dx. All right. So I'm looking at something that has a coefficient, an understood coefficient of 1, a variable, and a power. All right. This is a power relation. All right. So we would use the power rule. All right. So it's still a power rule. It's just a power rule for antiderivative instead of a power rule for derivative. You know, sometimes called the reverse power rule. All right. If you're thinking of the power rule as being exclusively for derivatives, this is the reverse of that. All right. So whether you're going by the actual rule, that power rule is the antiderivative of ax to the, I think I used n. What did I use there? Oh, I just use x to the n. Well, ax to the n dx would be equal to a over n plus 1 x to the n plus 1 plus c. All right. This variation of that power rule allows for a coefficient other than 1. So there's a benefit to that. We're just doing a little shrinky dinky. All right. So you could do that, or you just kind of talk to yourself. You know, it's kind of weird to think that talking to yourself might be the way to go, but in this case, I find that that's exactly the way to go. All right. So the power rule, I would say, okay, what do I do? Take my power, multiply it by the coefficient, reduce the power by 1. Let me do the exact opposite of that. So what's the last thing I did there? I reduced my power by 1, so let me increase my power by 1. So x raised to the -4 plus 1. All right. Again, the power rule for derivatives, take the power, multiply it by the coefficient, reduce the power by 1. So I did the opposite of the power part of it, where I increased the power by 1. Instead of multiplying by the coefficient, I'm going to divide into the coefficient. So 1 over -4 plus 1, all plus c. Now you can kind of streamline this. Well, you can really streamline it by kind of doing it all in your head. You know, at first that seems like a tall order, but the more you do it, the easier it becomes. So just resizing again. I really got to change the thickness on this marker because I can't just be doing this all night. So -1/3 x to the -3 plus c. All right. And you check by the power rule. Multiply power by coefficient, you get a 1. Reduce the power by 1, you get a -4. And the c would go away because the derivative of a constant is equal to 0. All right. So the reverse of the power rule should be kind of your bread and butter when it comes to anti-differentiation, because it comes up so frequently. You got to get to a point where it's like, okay, well, that's the easy part. Let me worry about the more challenging. All right. Number 2 has some exponential stuff in it, but it also has some sums and differences. The first thing that we want to do when you see a problem like this, and actually this comes into play repeatedly, it happens again in number 5, number 6, number 7, number 8. So basically, most of the problems on this page, you want to be either rewriting this so that they're separate integrals, or you want to just be thinking of them as separate integrals. So this would be the same as the antiderivative of 3 to the x dx minus the antiderivative of e to the x dx minus the antiderivative of x cubed dx plus the antiderivative of x to the e power dx. All right. You don't have to write this out. This is really just for your benefit, you know, like just so you understand the concept. But really what you should be thinking, just like if you were taking the derivative, you're going to want to think of these as different expressions that need to be anti-differentiated. And then once you once you carry out that process of anti-differentiation, you put it all back together based on the operation that's indicated, right? So I would look to my rules. If you don't know them, they're on that previous page. That first one, a to the x power, is some number other than e raised to the x power. So the rule is 1 over the natural log of a times a to the x power plus c. But that has everything to do with the fact that the derivative, so if you know your derivative rule, that's much easier, because in that case, we take the expression, leave it as is, but then multiply by the derivative of, by the natural log of the base. So here we're doing the same thing, but we're dividing by the natural log of the base, right? So this piece here would just become 1 over the natural log of 3 times 3, that's not a 3, 3 to the x, right? So that's my first piece. My second piece, that's easy because the derivative of e to the x is e to the x, which means the antiderivative of e to the x is e to the x. They're separated by a minus, or at least the integrand is. So my antiderivative should be separated by a minus, right? X to the third power, that's a power relation. So increase the exponent by 1, divide by the new exponent. So x to the fourth power, there's an understood coefficient of 1 here, divide that by 4, 1/4 x to the fourth. Whatever the operator is, that comes down to be part of the fund. That last little bit there, that x to the e power, it's kind of mean, but that's sort of a trick question. It's not sort of, it actually is a trick question. All right, so this one is a power relation. All right, so the power rule applies for that. All right, the reason why is the base is variable, the power is constant. All right, it's not like this one. Just because it has an e in it doesn't mean it's exponential. E to the x, constant base, variable exponent, variable base, constant exponent, that's a power function or power relation. So understood coefficient of 1, increase the exponent by 1. The best we could do there is just write e plus 1, divide by that new exponent, and then just tack on a plus c at the end, and you're good to go. Now, it's kind of weird to think about this. I'm going to get into just a smidge of theory here for a second, but we just found the antiderivative of 3 separate integrals, right? The first one was our 1 over ln 3 times 3 to the x. I'm going to write it here. You don't have to write it down. I mean, I honestly don't know what, if anything, people are writing down, but you don't necessarily have to write this part of it if you are writing. 1 over ln 3 times 3 to the x, technically, this integral would have its own plus c, right? But the plus c here could be different from the plus c for this one. So I would sub this with a little subscript of 1. Then this one, e to the x, would also have its own plus c. So c sub 2. Then this one would have its own plus c, so 1/4 x to the fourth. That would be different from the other, so I'd call that sub 3. And then this one, 1 over e plus 1, x to the e plus 1, would have its own plus c, all connected. So the question would be, where on earth did all those plus c's go? Right? Because really, in the end, you would have all of this stuff here, right? But technically, we really should have all of this stuff plus the C1 minus the C2 minus a C3, and then plus a C4, right? So in reality, this is what it should look like. You should have a plus C1 minus C2 minus C3 plus C4, all right? But when I said last time that C is known as an absorbing constant, what that means is that it absorbs all other constants, right? And that the idea here is, all right, well, what am I really going to end up with if I add, let's say, the C1 and the C4? Well, I don't know, but I know it's going to be a constant, right? What am I going to get if I take a negative C2 and subtract from it C3? They're two unknown constants, not necessarily the same thing. I don't know what I would get, but I do know that the result is going to be some kind of constant, right? So when you combine all these together, ultimately, they're just going to give you a singular constant, and they can be coalesced into that single constant, right? So the C would actually absorb C1 minus C2 minus C3 plus C4 into its collective, right? So it's kind of interesting to think about it that way, but ultimately, the reason why I was saying you didn't have to write any of this stuff down is because it really didn't amount to anything, right? It doesn't really matter for much because you're just going to get a plus C at the end. So why itemize it if you know you're just going to combine them all in the end? All right. So that's the idea there. And when you get at the fact that a negative C2 is really, it can also be thought of as a positive C2, that makes it even more mind-bending, because if I look at this, I could say, and I'll actually just write it real quick, kind of funny, math funny, I guess. You know, funny how the universe works, kind of funny. I could look at this as plus, too thick, C1 plus a negative C2 plus a negative C3 plus C4. But a negative constant is still a constant. So if I wanted to, I could call this like C5. And I'll call this, well, I'll call that one C6, I guess. So I would have the sum of four constants, but ultimately it's still going to give me a singular constant. Right? So just strange. I'll get to the chat in a second there. All right, so let's see, we got some stuff coming in here. Yeah, exactly. All right. So, you know, I mean, this is an example where, I mean, I got to teach the concept, I got to teach the theory, but in terms of just getting the answer, it's pretty quick and easy. This goes under the category of, wow, he's making this way more complicated than it needs to be. But that's just so I can explain the thought process behind all this stuff. Okay? But following the steps will get you there. That's never going to be an issue. Like, for example, in number 3, you know, there's none of that stuff. I could look at that 5 and say, well, that's a constant multiple. I can factor that out and make this 5 times the integral of cosine x dx, which we know by rule is equal to the sine of x plus c. All right. The only thing you got to be careful about is the sign, SIGN sign, because, and I'll multiply by the 5 in a second, because we're so used to taking derivatives, you see sine, you think cosine. You see cosine, you think negative sine, because that's what the derivatives are. We're just going the other way. So I'm thinking, what would I have to differentiate in order to end up with a cosine? And that would be a sine, right? And it also happens to be right here. But I'm going to take this, multiply it by 5. So that's going to give me 5 times the sine of x plus 5 times a constant. Well, 5 times a constant is still a constant. So plus C. All right. Because again, we're just putting it in its most general form. It's a constant C. All right. Number 4 is a differential equation. If you remember back to the discussion of differentials, when you take a derivative, it's automatically a differential equation, but we can get that differential equation into differential form, right? So we would do that by multiplying both sides by d theta. And so we would have dr is equal to pi d theta. All right. Now this is a change of coordinate systems. These are polar coordinates, but like that's not really important at this point. It's just we're using r's and thetas instead of x's and y's. Right. So that's fine. Pi is still a constant, right? But if I want to solve a differential equation, now this is a basic one. What I would do is anti-differentiate, right? Because basically what this is saying is I have the derivative, I want the original function, right? Now that dr could be thought of as a 1dr. An operation, an appropriate operation, just like you could take the square root of both sides of an equation, or you can multiply both sides of an equation by a non-zero value. You can also differentiate or anti-differentiate both sides of an equation. So I'm going to anti-differentiate here. All right. So on the left side, I'm anti-differentiating with respect to r, which means I'm taking the antiderivative and the relevant variable is r. Right? On the right, I'm anti-differentiating with respect to theta, which means I'm taking the antiderivative and the relevant variable is theta. Right? So if I look at this as a power rule kind of situation, let me rewrite. Assuming I don't want to just reference a rule every single time, I could look at this 1 as really 1 times r to the 0th power. Right? That's the same thing. It's a power relation. So take this expression, increase the exponent by 1, comes r to the 1st power, divide by the new exponent, 1 over 1, plus some constant c. All right. Now I have to anti-differentiate a second time, so I'm going to call this c sub 1. All right. Then on the right-hand side, that pi d theta, again, theta is a variable here. So instead of pi d theta, I'm going to write it as pi theta to the 0th power, right? Because again, it's still constant. Increase my exponent by 1. So it becomes pi theta to the 1st power. Divide by that new exponent, pi over 1, theta to the 1st. Now it's going to have its own constant that we'll call C2. All right. So cleaning this up, we would have R plus C1 is equal to pi theta plus C2. And so that's a solution to a differential equation, but I want to consolidate and clean it up as much as possible. Generally, I want to get an answer in explicit form, in that I want to have the equation solved for one variable in terms of the other. So I can subtract the C1 from both sides. It'll cancel on the left because anything minus itself would be equal to 0. So that part is fine. But on the right-hand side, they're not guaranteed to be the same number. But I do know I'm going to get some constant as a result. Now, it is possible that that constant could be 0. If it turns out that C1 and C2 are the same, it could end up being 0, but it could also be any other constant. So plus C. All right. So Desmos does have a polar mode. All right, these are polar coordinates. I can show you really quickly. We're not doing much with polar in here though, so this is just kind of fun fact of the day territory. But you can put it in, you create a polar graph, right? I could put in the function, but I'll just show you anyway. R equals pi theta. And you can put the plus c there, you know, some constant c. You know, just to kind of see what the graph would look like. Fun looking graph. Called the spiral of Archimedes, if anybody's wondering about that sort of thing. You'll do a lot more of that in Calc 3. But for now, it's just a fun looking graph, right? And it's a polar function, so it wouldn't be a function in a rectangular sense. You'd have to change a coordinate system to get the to treat it as a function, right? But the derivative of this I mean, that's an error. It's like try adding or equals to it, meaning we don't know what the hell you're asking us to do here, right? If you put it as r of theta here, it'll still give you the function, and then you can try it, r prime of theta, but it's treating theta as a constant, right? So it's giving us a result that's just pi. At a derivative value at theta is just given a result of pi. So basically, long story short, is Desmos will graph the function for you, like as in the result, but it has a hard time with the derivative, right? You try dr d theta. You know, nothing, right? So it's not really, Desmos wasn't really designed with derivatives of polar functions in mind. So for this one, it's more like, all right, check it the old fashioned way. But you could also get a look at the function itself and see what the story is there. Oh, actually, I just realized something. So it is true, Desmos does have a hard time with polar functions, but I believe in this one instance, it actually gave us the right answer. Because it just occurred to me that dr d theta was equal to pi, it was constant. So it actually worked out. Right, so r prime of theta, it just said it in a way that I wasn't expecting, right? But yeah, it's going to have a hard time. I mean, if you're looking for a graph, for example, you know, like it's not obvious. You know, if it's there, it's not easy to spot. Right. By the way, that's what it looks like if you zoom out. So it's different, right? But it can do some things with polar. Right? That's the moral of the story there. Number five and 7 really are interesting problems in the sense that they don't look like, and actually even 8, they're problems that don't look like they're the kind that we could actually do based off of our current knowledge base, but we can. Just you got to do a little algebra beforehand, right? So in this case, if I can get my pen to work, which it doesn't want to do. Sorry, I got to reconnect it. But break up the fractions, really what I'm getting at here. So if I take this fraction here and split it based off of the 3 components of the numerator, split it by the operation plus and minus, then I'll get something that I call it power rule ready. All right. So x squared over x to the 4th plus 2x over x to the 4th minus 3 over x to the 4th, all dx. So then get it into power form. So keep the base, subtract the exponent, x to the negative 2nd, right, plus 2x to the negative 3rd minus 3x to the negative 4th, dx with our integration symbol. And then anti-differentiate each piece by taking each exponent, adding 1 to it, and dividing the coefficient there by that new exponent. All right. So if I take my exponent -2, add 1 to it, I get a -1. Take this 1, divide it by that new exponent, I'm going to get a -1. So -x to the -1st. All right. Increase the -3 by 1, I get a -2. Divide this by a -2, I get my new coefficient, which is another -1. So -x to the -2nd. The -4, add 1 to it, you get a -3. Divide this coefficient by that -3, and I get plus x to the -3rd power, all plus c at the end. All right. So it was just a matter of algebraically manipulating it just a smidge to get it into a more appropriate form, or a more recognizable form more than anything else, but it's doable. All right. In this one, we have a power relation and we have a trig rule. So increase the exponent by 1, divide the coefficient by the new exponent, 1/3 x cubed. Antiderivative secant squared, that's a rule. Antiderivative secant squared is tangent. Bring down the plus, throw on a plus c at the end. Some of them are pretty easy, but that one is not easy if you don't know the rule. All right. Number 7, got to clean it up algebraically a little bit first, but that radical x can be thought of as x to the 1/2. I can take this x to the 1/2 and bring it up and make this 1/2 x to the -1/2. Anti-differentiate each piece. Increase the exponents by 1, divide by the new exponent. Again, understood coefficient of 1 here. If I increase a 1/2 by 1, I get 3/2. If I divide the 1 by 3/2, that's the same as taking the 1 and multiplying by 2/3. I'm going to get 2/3. All right. Increase a -1/2 by 1, I get a positive 1/2. Divide by that new exponent. Well, 1/2 divided by 1/2 is 1. So that's just going to go really not factor into the solution at all. Bring down the positive sign. And now I have my antiderivative. Just throw a plus c on it. All right. Number 8. Again, another situation where some algebra is required. But this is the kind of problem that people tend to struggle with in Calc 2, because you'll learn a bunch of different techniques to handle more advanced types of situations. And people have a tendency to try to overly complicate things. I don't know why, but they do. In this case, it's like, all right, well, let's just distribute this out and use the power rule. All right, because this is the same as saying 2t squared minus 1 times 2t squared minus 1. All right, so distribute it out, you get 4t to the 4th, minus 2t squared minus 2t squared, so minus 4t squared, plus 1. Anti-differentiate each piece. So increase the exponent by 1, divide by the new exponent. So 4/5 t to the 5th. Increase the exponent by 1, -4/3 t to the 3rd, divide by the new exponent. And again, attached to the 1 is an understood t to the 0th. Increase the exponent by 1, divide by the new exponent. Throw on a plus c at the end. All right. But then you have ones that look really way more complicated than they need to be, especially when you throw in a log. But these are actually very simple. First off, remember, you have the power rule for logs, right? Not power rule for derivatives, but power rule for logs. That tells us that we can take a power that's contained within the argument of a log and make it the coefficient. So I could rewrite this as 2 times the antiderivative of 2 ln of x dx. I could also factor out this 2. Doesn't need to be there. It's a constant multiple. So this is the same as saying 4 times the antiderivative of ln of x dx. This piece here is a rule. We talked about this last time. All right. So you have it, oh, it's somewhere here. X ln x minus x plus c. It's right at the bottom of page 69. All right. So 4 times x ln x minus x plus c is going to become 4x ln x minus 4x plus c. Because again, when you distribute this, it's going to get absorbed by that c. All right. So you still had a log rule in there, but it was actually just that. It was a rule. All right. So it was just a kind of a copy paste job. All right. This one, I guess I'm supposed to save the hardest for the last, but this is actually one of the easiest ones because again, the exponent hops over the log. This becomes 2 times the antiderivative of x ln of e dx. The natural log of e is equal to 1. So this is really saying 2 times the antiderivative of x dx. So it's not even really a log. It's actually a disguised linear relationship. Okay? There's an understood coefficient and exponents of 1. Increase the exponent by 1. Divide by the new exponent. Throw on a plus c. Still have that constant multiplier that comes along for the ride. Run through with that. And you get x squared plus c. All right. To think that x squared plus c would have a derivative of 2 times the natural log of e to the x is kind of weird, but that's only because we took a linear function and wrote it as a natural log. All right. Now, that's pretty much the extent of indefinite integration. Right? There's no bounds of integration. These are just skills, just finding antiderivatives, or at least for this course. What we're going to do now is focus on definite integrals, and this ties together with the Riemann sums and also really any other kind of approximation for finding areas. Right? So it's kind of weird that in the last couple of weeks of class, in this semester, we finally get to a rule called the fundamental theorem of calculus. You'd think that that would happen much earlier in the process, but here we are. So you can find the area under a curve if you know how to find the antiderivative by substituting the bounds of integration, the a and b values, into your antiderivative and subtracting the results. Right. So I'll give you a quick example. Let's say you have, for example, you want to find the area under a curve. All right. And let's say that that area is under the curve f of x is equal to x squared over the interval of 0 to 2. All right. So find, I'm going to write small. Well, I'm going to write normal size and then shrink it down. Bounded by f of x is equal to x squared on the interval of 0 to 2 Well, it's bounded by the function and the x-axis. I meant to write in there. I apologize. I got to squeeze that in there. And the x-axis on the interval of 0 to 2. All right. The way we would write that, at least a couple of days ago, would be using, or the way we would develop that solution would be using rectangular approximation. I'm going to try to find a way. No, it's not going to let me resize it. Okay. All right, timeout. It's just that it looks so terrible that I need to make it look a little bit better. And x-axis. A little bit more. Half this video is going to be me resizing stuff. All right. So find the area bounded by y equals x squared, the x-axis on the interval of 0 to 2. All right. So we did this with the rectangular approximation. We started off with 4 rectangles, then we went to 8 rectangles, and then after that, we're like, forget it, let's use limits. All right. But what we ended up ultimately coming up with was sort of a monstrosity. And let me show you what that monstrosity was. All right. It was the limit as n approached infinity of the sum from I equaled 1 to n. Now, we had a particular form, but I'm just writing the general rule. Right? So that was f of a plus I delta x times delta x. All right. So what happens is this whole process gets sort of streamlined, right? And the streamlining happens based off of just our knowledge of anti-differentiation, right? The connection is that when you find the antiderivative of a function, you are actually finding a function that represents the accumulation of area over an interval, right? It's just, in the case of the previous problems, the ones we did on the last page, it was over an unrestricted interval. So if I tell you that you have a boundless function, an infinite function, and then I ask you to find the area contained between that function and the x-axis, you might say, well, isn't it infinite? Doesn't that mean that there would be infinite area? And the answer is yes and no, because sometimes based off of the presence of asymptotes and things like that, you could have some finite area over an infinite interval. All right. I could show you one real quick. Normal? No, normal. Let's see, normal curve formula, that's the one. All right, so this function is the function of the normal distribution, right? So thinking in terms of statistics, if anybody's taken a stat class, you're definitely familiar with this. The area under this curve, even though it extends from negative infinity to infinity, I can get the axis in here, the grid and the axes. All right, the area contained between this curve and the x-axis is actually equal to 1, even though it's boundless. All right, it goes on forever to negative infinity. It goes on forever to positive infinity. All right, but because it's approaching 0, because there's a horizontal asymptote, it has a finite area. All right, so but that's a pretty particular type of exponential function. All right, it doesn't always play out that way. So if I tell you, like in this instance, that I have f of x is equal to x squared, and I don't restrict it, but then I ask you to find the area between the curve and the x-axis, you'd say, well, this thing goes on forever. Wouldn't that mean infinite amount of area? Right? So what we do is we restrict it. So I would say I want it to go from x equals a. I don't know why that happened. Let me type in the a equals 0 first. Then x equals a. Yeah, that's so weird. All right, so x equals some value of a, and then some b value. Put a 0 there. So x equals b. All right, so this would tell me, or at least allow me to determine a restriction, which would then allow me to figure out the area captured between these two bounded values. All right, so That's really what's going on there. Let me see if there's a way. Now, there's definitely a way to shade it. It's just probably a little too much for now. All right. So I would be looking for anything restricted over this interval from the green vertical to the black vertical. All right. But in this case, I want to go from 0 to 2. So I would place my green vertical at 0 and my black vertical at 2. And I'd be looking for this area, this little smidge of area here. Not a whole heck of a lot, but this is all I'd be interested in. All right. Now we've done this problem ad nauseum to the point where we already know what the answer is, but we want an easier way. Right. So what happens is this delta x represents some sort of change in x. All right. That change in x is the width of the rectangle. All right. So when we use rectangular approximation, we fit as many rectangles as we can under the curve, right? So n represents the number of rectangles. If that goes to infinity, then these two concepts really merge to give us a dx. All right. So then the rest of this, the f of a plus I delta x, that's evaluating the function. Remember, we started with a particular a value, and then we went a certain number of places to get to a b value, all right? So that gives us some boundaries. So an a to b value, all right? That was all substituted into the function f of x, all right? So what this is telling us is that that limit, that funky limit that we worked on previously, is equivalent to an antiderivative over the bounds or over the interval of a to b from the bound a to the bound b of the function f of x dx. So if I tell you the bounds are a equals 0 to b equals 2, I'd be looking at the antiderivative over the interval of 0 to 2. The function f of x is equivalent to x squared, and I still have my dx. This new expression here, this antiderivative over an interval, is equivalent to that limit. All right. So then what would we do? Well, we would anti-differentiate, just like we did on the previous page. We'd apply the reverse of the power rule. All right, I get an understood coefficient of 1. Increase my exponent by 1. Divide by the new exponent. All right, you'd have some integration constant plus c, but I'll show you why that doesn't matter in a second, but I'm going to put it down anyway. All right, so plus c. All right, but the thing is, we have now a need to restrict this over an interval of 0 to 2, right? So given that the vertical line means given, we're living on the interval of x equals 0 to x equals 2. Most people just write this with just the numbers. So you could do that if you want, but this is ultimately what we're looking at, all right? Because it's over the interval of x equals 0 to x equals 2, all right? And so what you're actually getting when you find the antiderivative at a particular point. So if I make a substitution, what I'm actually finding is the area to the left of that benchmark captured between the curve itself and the x-axis, all right? So what that would be in this case would be x is less than or equal to b. So it would give me, but also such that it's between the function. Let's see if I remember how to do this. 0 less than or equal to y less than or equal to f of x. Yeah. So it'd give me all the area to the left of 2. all right, like all of the area to the left of 2, like for all eternity, right? It would never stop going, right? So that's what a substitution of 2 into an antiderivative gives us, right? So that's what I'll do because that's useful information. At least it truncates it somewhat. So I'm looking at 1/3 times 2 cubed plus c. Can't plug anything in for the c. Now, if I find the substitution of 0 in for the x value, what that's going to give me is everything left of the 0. All right. So in this case, that's my a value. So I'm just going to do a quick duplication here and make this an a. And let's make this a lighter color. Oh, you know what? I got an idea. Make one red, make one blue. And now the overlap is purple. All right. So by plugging in the 0, I'm going to get everything to the left area-wise of the benchmark 0. Right. So if I slid my slider over, it would cover more area. Right. If I go to the left, it would cover less area. But I wanted it at 0, so I wanted to just the right amount. Right. So that's what I would get if I replaced the x with a 0 in the function. All right. So, but it's plus some constant, and since we don't know that constant, you know, it's all kind of a moot point. We just don't have that information. All right. But what we do is subtract these two values, because if I take this area and subtract from it this area, subtract from it the stuff I don't need, so this area, subtract from it the stuff I don't need, then I'll get the stuff that I do want, which would be just that red area. Right. And so that's the fundamental theorem of calculus, or at least the first part of it. But you'll see when I subtract these two expressions, since this c value is the same, it's actually going to cancel out. Right? This is the same constant in both cases. So I'm looking at 1/3 times 2 to the third, which is 8/3, plus c, minus 0 minus c. Right? Because these are exactly the same constant, when you subtract them, they actually do cancel out in this instance. Right? Leaving us with just an 8/3. And, you know, I don't know if you remember, but that's what the answer was when we did it with rectangular approximation. Right? So that's the long explanation, because most of the time it's like, all right, just plug it into your calculator. You know, I mean, do it by hand, but follow the rule. You know, the capital F, remember, it's antiderivative. So it's plug in the upper bound, plug in the lower bound, subtract the 2. But what this is telling us is that I never needed to have the plus c there. The plus c never needed to be there from the get-go. So I could have done all of this without the plus c, because it would have canceled out anyway. All right. But at least this one time I wanted to show you, that's always a question. All right. So anytime you have what we call a definite integral, you're taking the antiderivative and plugging in the upper bound, then plugging in the lower bound of integration, then subtracting in the order of upper minus lower. All right. So the higher bound, you know, physically and also numerically. All right. All that being said, Desmos has the capability, and so do the TI calculators, have the ability to anti-differentiate for you just as a native feature. So if you go into functions under miscellaneous for some reason, 0 to 2, it'll work with it in symbolic form also, like in the sense that if I put in f of x rather than x squared, I'm just trying to get this back to 0. All right, I'm about to give up because it doesn't really even matter. I just got fixated on it for a second. Open parentheses for your integrand. So I could do it as x squared. Close the parentheses, type in dx. Do a little fraction conversion there, right? But if you want, you can also do it antiderivative on the interval of 0 to 2 f of x. If you have the f of x already stored in, you could do it this way also. And I mean, if you really want to get cute, we have the a value and the b value representing the bounds. You could do it in its most general form. You know, so if you think about this, you know, like you can kind of set up, and I do have a Desmos for you on this, but you have a function. I don't need this anymore. You have your two sliders that represent your bounds. I like to have the shading in there. You know, I think it looks a little nicer. And then you have the antiderivative as a, well, it's a definite integral, but the one thing it won't do is it won't compute the antiderivative for you. It won't give you the 1/3 x cubed, right? But it will give you the result of the operation, right? So that makes things a whole lot easier, because a lot of the questions that you'll see involve properties, but in a lot of cases, you can just kind of explore using a Desmos like this and come up with these results. But some of the properties I think are obvious, and I say they're important properties, but some of them are just common sense, and some of them are a little weird, but they're all very doable. I just wanted to take a minute. I know I don't do this a lot, but I wanted to take a second and just do the antiderivative function on the TI for those of you moving on to bigger and better things. So in the math menu, you see two options that'll be important for you moving on. The numerical derivative and the function integral, right? So math option 8, numerical derivative. So if I needed to find a derivative of a function, if it's a TI-84, it should look like this. You just type in your function. So this is derivative. Put in the variable and put in the value you want to evaluate your derivative for. So let's say I want to find the derivative of a function when x is equal to 2. I would just put the number 2 in there, then hit enter. Right. So if you just I picked a simple problem so that we could verify it quickly. The derivative of x squared is 2x. You plug in a 2 there, you get 4. Right. But if I need to find the antiderivative, option 9, math option 9, you see it's picture perfect. It's ready to go. It's one of the things the TI folks got right, because it actually looks kind of, I know mine's an emulator, but it still looks really nice on the TI calculators also. But if you have an 83, it looks very different. So if you're taking Calc 2 and it's going to be an in-person course, you may want, and you have a TI-83, you may want to splurge for the TI-84. I don't want to spend people's money for them, but you know, if it's going to be a situation where you're required to get a calculator, the TI-84 does a lot of calculus stuff that the TI-83 also does, but not as well, right? So just public service there. But yeah, if I wanted to do, for example, this problem here, I would type in x squared, then I would type in my low bound, my upper bound, and then I would put in the variable, the relevant variable, which is an x. You know, the final answer doesn't look so pretty, but you know, it's equivalent. And just remember on the TI, it's an extra step to get it into fraction form. Math option 1, right? Converts it to fraction, you get your 8/3 out. Right. So, you know, we haven't really needed the TI for a whole heck of a lot, but I figured I'd definitely show you that one because that's going to be a big deal going forward. Right. But yeah, this is good. It looks extraordinary. Look how beautiful this is. But you know, if you're in person, I can't imagine that your teacher is going to let you get away with using Desmos. And only because it would involve you whipping out your phone in the middle of a test, you know, or some other device. If they want you to do a pencil paper, that's going to be an issue, you know. So if it's remote, then, you know, different story. You know, the party continues, but the same thing with online. But yeah, it is a shame that they don't have a physical calculator. But also, I know that they tried doing. They have this the testing version of the calculator. You know, like there's a testing mode that is supposed to make it secure, and it actually works. But the problem is there's too many excuses that people make up to get out of that mode, and it's just not tenable at this point. But we're getting closer. You know, unfortunately, it's just going to boil down to everybody here will have long since graduated by the time they figure it out. But you know, it is what it is. All right. So the first property here, if f is defined at x equals a, meaning it exists in some capacity, then the antiderivative or the definite integral over the interval of a to itself would be equal to 0. All right. And that should make sense, because what that's saying is no area has been accumulated. All right. So if I take my function and go from some a value to some other a value. So let me actually just go by the vertical lines here. So I'll say x equals a, x equals b. All right, so let's say I have my two lines, my two vertical lines, and they're at different locations. From the green to the blue, it's going to capture some area between the curve and the x-axis. But if the green and the blue are at the same location, no area will be captured. All right, it's a two-dimensional space, but it hasn't generated any area because they're identically located. In fact, we're taking a two-dimensional space and making it one-dimensional. Right, so we would not capture any area there. All right, so that's justification of the first one. Now, the second one, I think, is probably easier to just do it by just a quick rote computation. Cancel that. So let's say I have this same exact operation here. Let me get rid of these for now. This operation, the antiderivative over the interval of a to b. Right. So let's say instead of a to b, it's b to a. All right. Take note of what this decimal value is. It's about -1.68, blah, blah, blah. All right. But let's say we're going from b to a instead of a to b. All right. Same number, opposite sign. All right. So if I take the bounds and reverse them, it's going to create an opposite area. Right. As in the sign of the area would be the opposite. All right. The idea behind that, just a quick justification in geometry. Let's say you have an arbitrary function over an interval of a to b. So I'll say a is here, b is here. And over that interval, we have an arbitrary rectangle, you know, just thinking along the lines of the Riemann sums. All right. So this area would be generated by whatever the height is at this location. So this would be some value y, and this would be some delta x value, right? Going from left to right. All right. So that area would be some value of y times delta x for just that one rectangle, right? But because I'm going from left to right, delta x is positive, right? So left to right means that it's a positive result. Now, if I go from right to left, I'm changing my direction, the vector quantity, delta x would now be negative. So the area would still have the same y, the height never changed, but my delta x is now negated. So this would be negative y delta x for just that one rectangle. So then if I fill this area up with infinitely many rectangles, I'm going to have infinitely many of these negative y delta x's, the only difference being the direction, right? So if you're going from left to right, you're expecting a positive area if you're above the x-axis. If you go from right to left, you're expecting a negative area if you're above the x-axis. As opposed to, so let me just kind of switch it up here a little bit, as opposed to a graph that's below the x-axis. All right, I'm going to actually move that up real quick. So if I have a graph that's below the x-axis, still over the interval of a to b, you run into a little bit of an issue here with this whole logic, the reasoning going into that. And that is that below the axis, instead of a positive y giving us the distance, it would be some negative value of y, giving us the vertical distance. All right. So this would be a y, this would be a delta x. The area here would be negative y times delta x. And that's going from left to right. As opposed to going right to left, negative x would, negative delta x would be the movement. The area here would be negative y times negative delta x. So y times delta x. All right. So it's kind of weird, but the rules change when you're below the x-axis as opposed to above the x-axis. All right. So from left to right above the x-axis, you should have a positive area. From left to right below the x-axis, you should have a negative area. But all this rule here is saying is that if you reverse the bounds of integration, so your function is what it is. It's above the x-axis or below the x-axis, doesn't matter. Just crashed on me. All it's going to do is reverse the antiderivative, or at least a sign of it. Right? Let me just open an arbitrary file here, kill it, and then go back. It crashes sometimes, as you know. All right, so let me just show you that on Desmos real quick. So again, some interval over the interval of a to b, or integral over the interval of a to b. And let's say we'll just stay with the 0 to 2. I'm just going to type it because I'll be here forever trying to slide it over. And get these on. All right, so that's the red area there. Let me just do it this way just to clean it up a little bit. Because now that we're past the theory part of it, it should be a little bit better. Oh. That's weird. Okay, undo. We'll worry about that later. All right, well, anyway, so what we're looking at here, again, an area of 8/3. If I have the reverse of that, so swap my bounds of integration. So this would be the instance where I'm going from right to left as opposed to left to right. The signs get reversed. So now let me change my function so that it's strictly below the x-axis. Right? You'll see that the relationship is still true. All right, it's still one positive, one negative. Right, so to correct for that, you just negate one, and you get the other. All right. The additive interval property, I think that's probably pretty easy to. They're still trying to push through this update but it never works when they push it through. So that I got to keep hitting cancel, but then the app crashes. So it's a nightmare, right? So, well, anyway, over the interval of A to B, we're looking at a particular area that we would like to determine the value. But let's say I wanted to go from, instead of 0 to 2, I wanted to go from 0 to 2 and then 2 to 4. Right. So let me get some kind of constant C in here. And I'll just make it a 4. So X equals C. So let's say I wanted to bring it out here. What this rule is telling us, the additive interval property, is telling us that I can take my desired area, right? So everything except for the purple, so all of this stuff here that's shaded in red, I can take that and add to it that little extra 2 block width area, put it together, and I'll get the total area over that interval, right? So we could break it up into parts, is what it's saying. So by some value along the way. Constant multiple, we've kind of beaten that to death. Additive function property, we took care of that on the previous page. Preservation of sign, that was addressed over here. And preservation of inequality, that's an interesting one, but I can just kind of rough that out for you real quick. If I give you a function over an interval of A to B, it's going to contain some area. Spoiler. Right, so it'll contain some area. And we'll call that function f of x. All right. Now, if I tell you that there's another function over the same interval that has a larger value, we'll call that g of x. All this rule is telling us is that it's going to contain more area. That's what I was saying before when I was saying a lot of these rules are just common sense. Because if I'm telling you that the antiderivative over an interval, or the definite integral, is telling us how much area is captured by a function in the x-axis over that interval, if I move the function further away from the x-axis, it's going to capture more area. So if I make the function taller, it's going to capture more area. That's all this rule is saying. Okay? It'll never be a situation where you move a function further away from the x-axis, but somehow end up with less area. It never plays out that way. Right? But these problems on the next page involve this idea of the fundamental theorem along with the properties. So depending on the information that you're given, it could be pretty easy, but sometimes it's pretty challenging, because it's a little mind bending. But for example, just jumping right to C, see that the bounds of integration are the same. Doesn't matter what the function is, that's going to be equal to 0, right? You haven't moved horizontally. Your delta x value is equal to 0. So there's nothing there, right? So that's a nice one. This one here is the additive interval property. What this is saying is, and I'll just kind of look at it in the form of a number line. If I have a number line going from 0 to 6, and it stops at 3 along the way, and I tell you that from 0 to 3, I have a certain area. I'll use a highlighter there because this is looking kind of stupid. And then I tell you going from 3 to 6, you have another area. And let's say over that first interval, the area is 4. And the other interval, the area is a -1. Right? So part of the graph is below the x-axis is really what that's saying. Stop it. Then what I can do is just add these two things together. But really, ultimately, what this is saying is going from 0 to 3 of f of x dx plus 3 to 6 of f of x dx will get us where we want to go. And since I know that going from 0 to 3 gets me a 4, and going from 3 to 6 gets me a -1, then the accumulated area would have to be a -3, right? Now, again, this goes back to what I was saying before. How can I have a negative area? Well, there's two ways that could happen. One way would be if I were working from right to left as opposed to left to right, which isn't happening here. The other way would be if part of the graph were below the x-axis, right? So what this is saying is that perhaps you have some kind of graph that looks like this, where over 0 to 3, let's say that this is 3 and this is 6. You have some accumulated area, you got some nice accumulated area, and then it's kind of like a little bit below the x-axis from 3 to 6. All right, so this amounts, I'm just making it up as I go here, but this would be the 4. This piece here would be the -1. Combined, that would give you an area. We call that a net area of -1, right? Because the thing is, when we talk about areas in a graph versus what it means contextually, now what we figure out here isn't actually the combined area of these two regions, right? Because if you think about it, we really should be looking at absolute values. If I tell you that this is a bounded region and this is a bounded region, and this one has an area of 4, this contains space, and it would be some positive amount of space. It's just its location puts it below the x-axis. So really, I would have a total of 5 units of area, because I would think of this as a positive number, right? But when we find a definite integral, we're finding what we call a net area, because it's an accumulation model. And so the way we kind of look at it is, or at least the way I explain it, is based off of it. It's kind of strange, but let's say we get a foot of snow. All right, you have a volume. It would actually be volume in that context of snow, or maybe a certain area of the ground is covered with snow, if you want to think of it that way. All right, and let's say that area is 100 square miles. All right, it's really not a whole heck of a lot, but let's say it's 100 square miles. All right, so that would be the area over that interval, maybe over a course of like 2 hours, of snowfall. That amount of area was covered. But then over the next 2 hours, the snow stopped and some of it started melting. All right, the amount of snow that melted away would be now the relevant area. All right, so we would now take into account how much snow melted, or what area no longer has snow. That would be the negative area. And put it all together, you now have the total accumulation of area related to the snowfall. All right, so it's weird, but there is an application for it. All right. But B is super easy, barely. So it's the bounds are the exact opposite of what we want here. So I can reverse them as long as I remember to negate the integral. And they told me in the setup here that this expression is equal to -1. So -1 would be equal to 1. So that would be the equivalent of finding this area. Instead of going left to right, I would go right to left. All right. And the last one that we'll do tonight is D, because that's the easiest one, and it's a nice way to finish. I have a constant multiplier of -5. I'm going to pull this out. Now I have the integral over the interval of 3 to 6, which was given to me as a -1. -5 times -1 is equal to +5. So what that gives me is an area. Now, contextually, it's kind of weird to think about, but what this means graphically is if I were to take my function, negate it, and dilate it by a factor of 5, this is what the area would be, right? So if I take my function, instead of, let's say, this x squared, if I made it negative 5x squared, that would flip it over the axis and make it skinnier. But it would also take my area and multiply it by the corresponding value. If you remember, for the x squared function, the area was 8 over 3. It's now negative 40 over 3, right? The 8 over 3 was multiplied by the constant multiple of negative 5, right? So it's a little demonstration of how that works, all right? So only a couple more topics to cover in the course. Really not a whole heck of a lot to do next class. So yeah, well, we're just going to wrap up the fundamental theorem, and that'll be it. Be on the lookout for the video solution for the review, the practice test. I mean, I posted it today, so you can start having a look at that if you haven't already done so. Just remember, it's due the midnight before the unit test. And so I'm going to stop the recording.